Hello, I'm Felix. I'm a first-year master's student in the FAR Data Lab at the University of Toronto. Today I'll be presenting PD3, a collaborative work between Sid, myself, Umayrah, Sherman, Jiasheng, Jialin, and Qizhen from the University of Toronto and NUS. Modern data center workloads increasingly demand lower latency and higher throughput. As a result, many cloud applications have moved towards in-memory designs. This provides significant performance benefits when the entire working set can fit within the host's physical memory. However, if the working set grows to be larger than it, significant slowdowns are observed due to the costly secondary storage accesses incurred. As a result, demand on physical memory is growing quickly. Furthermore, memory is a notoriously inelastic resource. It is tightly coupled with compute and monolithic architectures, and this has a couple of drawbacks. First, applications are incentivized to over-provision memory in order to prevent out-of-memory errors as the working set grows. And second, due to tight coupling, applications need to scale compute simultaneously with memory. This leads to further over-provisioning, and as a result, cloud services such as Azure and Google Cloud show significant memory utilization, as you can see in the figure on the left. Furthermore, with the recent rising prices of DRAM, we see this leads to a corresponding rise in the actual cost of this memory underutilization. To address this, memory disaggregation is a promising solution. While traditional monolithic architectures tightly couple resources, when using a disaggregated architecture, we have resource-specific pools that are connected via a fast network fabric. Compute pools have high processing power with a small amount of memory, which serves as a local cache, while memory nodes have a large amount of memory but are equipped with very weak CPUs. Memory disaggregation allows applications to elastically scale up memory, significantly reducing utilization and simplifying data center operations. However, despite improvements in networking, accessing disaggregated memory remains a costly operation compared to local memory. While local access may take in the order of 60 to 80 nanoseconds, and is done entirely in hardware, accessing disaggregated memory has a 4 to 10 microsecond network overhead. Furthermore, memory disaggregation today requires software support, which may blow up this overhead further and increase stack overheads, tail latency, and variance. A wide variety of recent work has attempted to address this, some of which I've listed on the right here. We can view this performance overhead through the lens of caching, with cache misses being the sole cause of the aforementioned performance degradation. If an application mostly misses its local cache when accessing data items, it will experience a large performance slowdown. However, if most accesses are in fact cache hits, performance degradation is minimal, even when using disaggregated memory. And we've seen a 10 to 100x improvement in this case. Thus, the overhead disaggregated memory can be framed purely as a cache miss problem. And this is what recent work like Leap and Hop, this is the line of reasoning they take. However, there are many cases where cache misses cannot be predicted via access patterns alone, as is done in current work, such as with cold starts or irregular accesses. We tested this empirically and on workloads with hard to predict cache access patterns, for example, uniform reads on a disaggregated hash map. Even a system with an optimized prefetch path and it was using Leap, we see a large throughput drop in the presence of cache misses. We aim to answer the question on how we can keep performance high even in these difficult scenarios. So we see that incoming client requests generate high numbers of cache misses and overhead in the classic case. We, however, now have this new networking hardware that's rapidly gaining popularity in the cloud data centers, the DPU. And the time it takes the execution engine to access the items based on a request, by taking advantage of the DPU's ability to see client requests before they reach the host, can we use the DPU to prefetch any missing data items and place them in local memory, such that the cache hit rate for the client application is now 100%. Before I dive into that, I'll quickly introduce a DPU. These are SoC-based smart NICs that come with general purpose compute, hardware accelerators, and onboard memory. They provide generally programmable compute that is tightly coupled with the network path, a significant opportunity. But they are constrained by weight P CPU cores and lower memory capacity and bandwidth when compared to those available on the host. So, for us to talk, I'll address the 3 challenges PD3 needed to tackle. The first is how do we determine what to prefetch? The second is how do we prefetch those missing items efficiently? And the third is how do we actually serve those prefetched data items quickly to the application? So, once a request arrives on the DPU, before it can actually prefetch any data, it obviously needs to determine what needs to be prefetched. So this is the responsibility of our host view. This is required because of the PD3's location on the DPU. We don't have native access to the items cached in local memory. Thus, the responsibility of the host view is to track those very items. The key challenge here was to ensure that the lookup matches that of modern data systems, which I will describe how we achieve that. But first, the host view is just a bucketized hash map. And once a request arrives, we're able to parse it to determine the keys that it will access. In this case, here the client has provided batching, so we can see that it will try to access these 4 keys. In support of this, we also support multi-key lookup. And then we follow very standard hash table semantics. So we begin by hashing each key to the corresponding buckets. We then use SIMD to quickly compare a key against all of the slots in the bucket. And then we output the missing data items that will need to be prefetched. As I mentioned, the key challenge here is to ensure that while running on the WinP's DPU's compute, the host view does not become a significant bottleneck. So to achieve this, we use some techniques I've already mentioned, where we do batching and SIMD for lookup. In addition to using huge pages, we delay unnecessary evaluation and sharding. This enables us to achieve a throughput of 70 million operations while running on the DPU, which is a 13x improvement over our baseline, as well as an order improvement over off-the-shelf solutions, such as this C++ standard template library, as well as Absol, a highly optimized implementation. So we're able to quickly determine whether a key is missing. However, how do we actually know that this is correct? So for the sake of time, I'll only be considering false positives here, which in this case is when host view incorrectly attempts to prefetch an item that's already cached within the compute server's local memory. There are 3 operations which may cause such an issue. The first is a write operation from the client. Now this is easily handled because this write operation necessarily traverses the NIC, at which point PD3 can intercept, parse the keys, and then update host view correspondingly. The second, similar scenario, is when they perform a read operation from disaggregated memory. As before, we can intercept this request and update the host view accordingly. The third case, where a false positive may occur, is when the client, or the execution engine here, silently generates an item and stores it locally. This is an issue because on a subsequent request, host view will believe that this item is not cached and generate a read request to disaggregated memory for that data item. This does not actually cause a false positive because since the item was generated silently, only on the compute server, the disaggregated memory will not find this item, and thus no item will actually be moved from disaggregated memory into the compute local memory, and thus no cache pollution actually occurs in this case. So this handles all 3 possible scenarios for false positives, which means that PD3 guarantees that one will not occur, and thereby completely prevents this source of cache pollution. So we've now efficiently determined what we need to prefetch. How do we actually do that? Well, this is the responsibility of our transfer engine. As we have a very tight latency, because we want to prefetch items before the execution engine goes to access them, we want to avoid unnecessary hops within our prefetch path. So once the host view determines items to be prefetched, it writes those directly into a DPU local request buffer, which then a separate thread will use and copy these requests over to disaggregated memory of RDMA. The disaggregated memory will then respond and write any prefetched items into a response buffer, also on the DPU. And then we will use DMA to transfer these responses into the actual compute server's local memory. Now note here we're actually using two different transfer protocols for responses. First we take RDMA to transfer from disaggregated memory to DPU memory, and then we use DMA to transfer from DPU to the compute server. To prevent an additional copy on the DPU, we use a unified buffer, ring buffer, where the underlying memory is registered with both the DPU's RNIC and its DMA engine. This enables us, during runtime, to seamlessly transfer data between these two protocols, RDMA and DMA, without any additional overhead. So we have now managed to efficiently prefetch data items from disaggregated memory into local memory. Finally, we actually need to serve these to the execution engine. And this is the responsibility of our loading zone. This is a highly concurrent buffer which quickly serves data items to the application. It reduces contention on the head and tail pointers for the ring buffers that we actually store our responses in, that many state-of-the-art ring buffers today doesn't handle. Finally, the application can use check and return, which is a form of non-blocking polling to quickly determine on the data path whether an item has been prefetched or not. So with all three questions answered, we'll now go to our evaluation. Here we have a two-server setup, and we extensively evaluated this over a couple of different applications. For the sake of time, I will only be discussing Garnet, a production key value cache out of Microsoft. So we compared our end-to-end performance with a host-based RDMA implementation, Leap, a prediction-based prefetcher, and Ready, which is a high-performance remote caching system. And we can see that we significantly outperformed them in both terms of throughput and latency. And if we look into why, here we have a breakdown of the actual request time that Garnet took. We see that PD3 completely eliminated the request and transfer times. This is when we managed to hide the latency entirely through our prefetching. This is further reinforced by our ablation study, where we see that if we remove prefetching and just leave the RDMA offload, we see a significant decrease in performance. And even more notably, with prefetching, PD3 achieves equivalent performance to a local version where the entire working set is stored within local memory. And then finally, if we look into it a little bit further, we see on the right-hand side of this graph the performance of RDMA and PD3 when there's 16 gigabytes of local memory, which can hold the entire working set. And PD3 is able to actually match this performance with only 128 megabytes of compute local memory, which is less than 1% of the total working set size. So to summarize, memory disaggregation incurs significant performance penalties due to cache misses and the corresponding remote memory access overhead. By leveraging the capability of DPUs and the location on the network path, PD3 determines cache misses for incoming requests and prefetches the required data items before they're accessed by the execution engine. And then finally, by using PD3, disaggregated applications can reach performance parity with their monolithic counterparts with minimal compute local memory. Thank you, and our code is available publicly here.